thing about exponential functions is that they're really useful for real life problems. A lot of things in nature, in particular, like biology class, grow or decay exponentially. So let's look here. So you suppose you have a function f of x is equal to a b to the x, and a is going to be greater than 0 because in real life problems, you almost never have a negative a to begin with. You start off with something. A is like your start off amount, your y-intercept. Okay, so and then we're going to talk about, okay, if a is positive always, that means you're always above the x-axis. Not like this. Oh, actually, I don't have one in here yet. This one right here, where everything was negative. We won't be having that for these particular types. Okay, so I wanted to give you some classic examples. So the classic examples are business, money, debt, and stuff like that, and populations and stuff like that. So let me give you an example. Suppose you have $10,000. If I could type, invested in an 8%, 7% savings account. Okay, what would that look like? Okay, well, the amount in your account would be equal to your starting amount, which is $10,000, not $100,000, $10,000 times. Now, if it's a savings account, your money's going to grow. You're going to accrue interest. So it's got to look like this one on the left. But to look like that one on the left, it's got to have a b that's greater than 1. 7% is not greater than 1. 7% is 0.07. Okay, so how can you make it greater than 1? The answer is you go 1.07. Oops, sorry, I had to pause there for a second. So let me just reiterate. So you have 10,000, so that's your starting amount right there. And then you have your base b, and it's got to be 1.07. And the reason being, you need it to be larger than 1. 0.07 is not larger than 1. 0.07 would mean you're losing money, right? Every year you have 7% of your 10,000, but you don't want to say that. You want to say, hey, I've got the 7% plus 100% of what I originally had. See, the 1 times 10,000 gets you 100%, and the 7.07 times the 10,000 gets you the extra 7%. So you basically have 107% every year. Now the interest rate is 7%, but what you actually have is 107% because you have 100% of what you had and the extra 7% there. And then to the x or t or whatever. Okay. Now what would that look like if I graphed it? Let me go grab a graph. Ugh, that's not a good graph. Hold on one second. There we go. So you can see it starts at 10,000. That's where it hits the y-axis, and it goes up, 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 right? So it's increasing by 7% each year, going up. And you can, if you don't believe me, look what I had to type in. 10,000 times 1.07 to the x. It's got to be 1.07. Just for the fun of it, let me just show you what would happen. If I did 0.07, that's what it would look like. It's going down, significantly down, right? Which is not what you wanted at all. Okay. All right, so that's what it works like for bank accounts, interest accounts, stuff like that. They all look like that. Okay. Now, what about decreasing? Oops, hold on one second. What if you had, suppose you have $10,000 in debt, like say like a student loan debt or something, and you are paying off 5% of it each year. What would that look like? Okay. Now, what most students try to do is they try to say, and I kept the 10,000 because, who cares? They'd say, oh, it's 10,000 times 0.05, which makes no sense at all. Let me show you what happens. It's like, oh, look, in 1 year I have all my student debt paid off. That's not going to happen, right? That's not how it works. Okay, so what's going on here? Well, the answer is it's going to be the difference between, let me put it this way. If you're paying off 5%, then how much do you have left? It's not 5%, right? So if you're paying off 5%, then you have 95% left each year. So instead of 0.05, you say 0.95, because you always care about the difference between that base and 1. I'm getting a little bit ahead of myself because a lot of this stuff is in the next section, but that's okay. We'll see it both times because it's kind of hard and tricky. So you want your b to be a fraction between 0 and 1 for sure, but if you have you have $10,000 in debt and you're paying 5% of it off, then you have 95% of it left. Let me show you the difference between that one and 95%. So 95 would look like that. Much more sensible, right? It takes you years to pay off your debt. Okay. Let me make it red. Red is fine. All right, I'm going to copy and paste. Okay. There, I made it a little bigger for you can see. So you'll notice what matters for your base is actually what you're multiplying by. You're not multiplying by 7%. You're multiplying by 107%, right? You're not multiplying by 5%. You multiply by 5% and then you take it away from 1, right? So in other words, you've got 95% of it that you're really multiplying by. What matters is how much is remaining, not how much you're trying to take away from. Same thing with this one up here. What matters is that you're going to have a larger amount. So you don't want to just multiply by 0.07. That would make it smaller. You want to multiply by 1.07. You want to make it bigger. How much you have remaining is bigger than 10,000. So you better be able to multiply by something that's bigger than 1 so that it'd be bigger than 10,000. All right, and again, we're going to see this more later, but just a reminder, right? If you want to make it grow, you've got to have a base be bigger than 1. That's what it says right there, be greater than 1. For growth, that's this. For decay, and that's the other one. Let me give you this. Growth. Okay? So to grow, you have to have b greater than 1. For decay, you have to have 0 is less than b, which is less than 1. It has to be a positive number, but between 0 and 1, like 0.95, 0.23, 0.67, stuff like that. That would be decay. All right, now let's look at the y-intercept. When you have a function that's a b to the x, then that automatically means that the y-intercept is, do you know it? Should. We've seen it a couple places. Well, here, heck, I saw it right here. Look where those graphs are hitting. 10,000, right? Because look at your value right there, 10,000. If you have, right here, 0, 2, that's because 2 was your A. Or look here, 0, 8. 8 was your A. That's why it hits the y-axis. Look at that, right at 8 on that dot. And this one was 4, 0, 4, because 0, 4 was your y-intercept, 4 is your letter A in front, and that's where it hits the y-axis. So hopefully, by this point, everybody knows that, and I actually wrote it right here. 0, A is the y-intercept, right there. So your y-intercept is 0, comma A. All right? All right, so let's look at this one. For f of x equals negative 3 times 4 to the x, describe the base multiplier property in words in a table. So let me give myself some values here. So I want x, and I want f of x equals negative 3 times 4 to the x. Okay? All right, now I know 0 is always a smart number to pick. And I'm going to put it right there. And if you're wondering why I'm doing that, well, here, clear this out. Negative 3 times 4 to the x. All right, so then let's see here. It goes second table. And I can see, oh, okay, I don't really have much good on the negative side. So negative 1 went to, let's see, negative 0.75. 0 went to negative 3. I know that without even looking. See? Negative 0.75, negative 3. And then the next one is negative 12, which everybody should know that because that's the whole point of the base multiplier properties, that I multiply by my base, which in this case is 4. So 48, and then 3 would go to negative 192, and 4 would go to negative 768. Again, they're right down there. There they are. Okay, so I got those in there. Fabulous. All good. So I've shown it in a table. Now what's happening in words? There we go. Every time the x increases by 1, the y, or let me put it this way, the f of x, f of x, here about this, f of x is multiplied by 4, because 4 is the base, right? So every time my x increases by 1, my y is multiplied by 4, because 4 is my base. Boom. So there's words. And there's the table. Now, is this function growing or decaying? Tricky. You know what? Let's look at a picture of it first. Let me go grab a graph. There we go. Okay, so what do you think? Growing or decaying? Now, it's not sitting up to our normal standards, because we normally said growth and decay is when a is positive. See how a is positive in these ones? Right? Bigger than 1. But for this one, a is negative. It's -3. But what's happening to this? As we go on, as x goes along, the y is plummeting. So this is actually exponential decay. All right, find the y-intercept. Well, it's kind of easy. It's 0, -3. Now you can see it in the problem because it said a was -3. It says -3 times 4 to the x. And then you can see it in the table right here, 0, -3. Right? And then you can also see it in the graph. Okay, so there's a lot of ways to see it. 0, -3, all good. Now we graph the function by hand, which I actually did this in reverse order, but there you go. Now by hand just means plot the points and then draw a curve that connects them. And for me, you want to fit, all these good points over here. That 2 should get in there, that 1 should get in there. You want to fit those in. The 3, -192 is too big, but you should be able to fit the other points in. And then these get too small. So you only get a few points for these curves. Now what's the domain and range? Domain, let me remind you, goes left, comma, right. And it can be brackets or parentheses. So it's just left or right. That's a domain. It's all the possible x's. And of course, x might not be x. It's all the possible inputs. Let me put it that way. So if you look at our graph, it goes forever to -4. I mean, if I go back to my table, it'll let me keep going and going and going up, right, for forever. So it goes on forever that direction. And similarly, down, 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 it goes forever that direction too. So it has all real numbers as the domain, because this thing keeps going forever to the left and right. Technically, I should have little arrows here. Unfortunately, I can't do them in that graphing program I use. So there should be an arrow pointing that way to the left, and there should be an arrow pointing that way. All right, now the range is all the possible outputs, which would be like your y's. So that's as far down as your graph gets to how far up it gets. Okay, well, again, there should be a little arrow here. It should be going forever to the downward direction. Right? You go forever and ever and ever and ever, no problems. So that's negative infinity is the downward direction. No problems there. Now the upward direction is where it gets interesting. It kind of comes up to this x-axis and then skims along it. It never really touches it. You can see that when you look at the table. So you can see as x gets negative, let me show you. It gets to be smaller and smaller and smaller decimals. See that? But it's not 0. It's -0.00, -0.000, -0.000, right? And so on. Okay? So you're getting smaller and smaller decimal values. So what does that mean? Well, it means it gets up to 0, but it never actually gets there. So that means that both of those deserve parentheses. Remember, the only time you get to do a bracket is if you get a closed dot, which you do not have in this case. So there you go, -infinity to 0. All the way up to 0, but you don't actually get to 0. So 0 itself doesn't count. All right, so we're done with the domain and range. Remember, range is y's and domain is x's.